Okay, good afternoon, statics class. I'm just going to go through and do a method of joints. We didn't finish it today in class, so we're going to just step through it, and that way, as you're working through your homework, you can follow through on a video. Well, this is the wrong one. Ignore that it just says BD, CD, and CE. We want to find determined force in members. How about we say in all members, and indicate whether they are in tension or compression. Okay, so step number one, remember, was to do a free body diagram and equilibrium of the whole so that we could get reactions. And we need to look, and at A we have a pin, and at F we have a roller. So we're going to have AX, AY, and FY. Then we need to isolate a joint with either one or two unknowns. We can't have more than that because all we have is summing forces X and summing forces Y. And then we're going to repeat until we have them all. Okay? So the first thing I'm going to do is draw a free body diagram of the whole. I'm going to label, my dimensions. I don't need to draw the inner part because right now I'm just looking at the external forces and the external reactions. And then we have AY, AX, FY. And we can sum forces in the X direction. And I can find that AX equals 0. And I can sum moments about F. Okay, right here is at F. So I'm going to have minus 120 kilonewtons times 6 meters plus AY times 9 meters equals 0. So I get 9 AY equals 120 times 6. It's 720 kilonewton meters. Divide through by 9. And I get 80 kilonewtons. Positive value. So I know my assumption going up is correct. So this is 80 kilonewtons. And I can go around and I can look at this now. And I can see, well, this has 1, 2, 3, 1, 2, 3, 4. I don't know this reaction yet, 1, 2. Here's a 0 force member, 2 unknowns, but I don't have any forces to go with it. 1, 2, 3, 4. I'm going to start right over here. Okay, so I'm going to call this free body diagram at A. And when I do this, if you need to, take a post-it note or whatever it is that you have handy. And we're going to cover everything up but that joint. And if I want to, I can go ahead and draw on there. Both of mine, we're going to assume they're in tension. So at A, I have 80 kilonewtons from my reaction. I have a member going to the right, and I have a member going up diagonally to the right. And I'll need to go back and look, and I can see that it is a 3-4 slope. And I'm going to call this one force CE, and this one force AB. Okay. This has both X and Y components, X component, and a Y given force. So if I start with summing X, I can find the relationship between these two, but I don't have a value to put with it. So I'm going to start with summing forces in the Y direction, and I have 80 kilonewtons, plus in the Y direction 4/5 FAB. And all of that has to equal 0. So 4/5 FAB, do my algebra, negative 80 kilonewtons. So FAB equals negative 100 kilonewtons. FAB equals 100 kilonewtons in compression. Okay, I can either call it negative 100, but that makes the assumption we're all on the same page, that compression is negative and tension is positive. And there might be one quirky person who wants to do things backwards. So it's just safer to let us know that it's in compression, use the magnitude, and tell us compression or tension. Okay, so at this point, you can either call this a negative 100, and when I sum forces in the x direction, if I want to sum forces in the x direction, I can have FCE plus, okay, I've assumed it this way, I found it's negative, but we're going to just call it a negative 100. So we're going to keep it in that positive tension direction. So I have plus 3/5 FAB. Well, FAB is negative 100. And if I work it out this way, I'm going to get that why am I calling this CE when this is so clearly AC? I don't even know where that came from. Okay, FAC equals a positive 60 kilonewtons, which means it's in tension. So that would be if I keep it as a negative and I don't change my shape direction up here. I am quirky, and if it is negative, I like to show the direction. Okay, so I literally am going to change the direction, and then when I sum my forces in the x direction, I'm going to get FAC, and then I can visually see it's in compression, it's pushing, so minus 3/5 times 100 kilonewtons. And this time I'm using that positive value because I'm directionally showing you that it's in compression. So either A, leave it in tension and use the value of negative 100, or B, show that it is in compression. And then I'm going to use the magnitude. Either way, you end up with a negative when you're looking at the x component of that force. So I get FAC equals 60 kilonewtons, which is tension. It's positive, so it's tension. So now what I'm going to do is go back up to my figure, and I'm going to let you know that this is 60 kilonewtons, and this is 100 kilonewtons, and this one's in compression, and this one's in tension. And now I can look, 1, 2, 3 unknowns, not helpful. 1, 2, there are now 2 unknowns. So I'm going to go up here to joint B. So here we have a free body diagram at B. Okay, and I'm going to take my little post-it note, I'm going to get a cut like that, I'm going to see, okay, I have this compression member coming in, I have these 2 unknowns, and I'm going to assume that they are in tension. So here we go, 120 kilonewtons, and then I have the force in BD, I have the force in BC, I'm assuming tension, and I have this compression member coming in at 100 kilonewtons, and it continues to be a 4-to-3 slope. Okay, I'm going to call it a positive, I'm going to call it a magnitude of 100, but I'm going to show directionally it's in compression. The other option would be to show it in tension and call it negative 100. You're going to get the same answer, but you can't mix these two methods. I show it's in compression. Okay, so now I'm going to start with summing forces in the x direction, and I get 3/5 times 100 kilonewtons, and I'm going to come around plus FBD equals 0, so FBD equals negative 60 kilonewtons. Okay, that tells me that we are in compression. We assumed tension. This is actually in compression. Because this is in the y direction, I'm going to go back up here, and I have 60 kilonewtons in compression. Okay, so now we can sum forces in the y direction. I'm going to call pushing upwards positive. So I have negative 120 kilonewtons, okay, minus FBC plus 4/5 fifths times 100 equals 0. We want that to be a positive value, so we have force BC equals negative 120 plus 80 kilonewtons equals negative 40. So FBC equals negative 40 kilonewtons, which equals 40 kilonewtons in compression. So I can go back up here and I can put on here 40 kilonewtons in compression. And if I want, I could just do a quick check. Let's just thumb X's. If this is compression and that's compression, they're both pushing in, so they're equal and opposite. So I can take 100, 3 times 5 divided by is 60. This one's actually pushing in, minus 60. Perfect. I have 120 that's going down. I have 80 that's going up, which means I have a negative 40. So that means this member does indeed have to be in compression, so it's pushing back up to keep it in equilibrium. Okay, there we go. Okay, so you just have to remember that compression means it's a member that is, it's wanting to be smushed. Okay, it's got loading and wanting it to be smushed. And because it's wanting to be smushed, it's kind of like pulling this joint over here and pulling this joint over here. And those joints are having to pull back, pull back. So that's why we have that force pushing it on the joint. Okay, if I have a tension member, it is wanting to stretch, 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 stretch. So the joint is having to push, 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 push back on it to keep it in place. And that's why we pull, that if it's in tension, it is pulling away from the joint. Okay, it's not the joint that's in tension, it's the member that's in tension. But because the member is wanting to go this way and that joint is having to push back, we can show that force pulling away. Okay, so now we have this done and this done. So now I can go 1, 2. So I could go to joint C. 1, 2, 3, 3. But I notice this is a 0 force. If I go to D, this has an XY and an XY. I'm going to end up with 2 equations, 2 unknowns. If I go down here, I can solve for the Y component, which clicks this member, and then come back and do X. And I don't want to have to do 2 equations, 2 unknowns if possible. So let's look at joint C. At C. Okay, so at C, I have 6 kilonewtons in tension. Tension is pulling away, 60 kilonewtons. I have 40 kilonewtons in compression. Compression is pushing. I have the force in CD, and that is at a 4-3. And then I have the force in CE. So I have 2 unknowns and I have 2 equations. We're going to start with summing forces in the Y direction is up. So I have 4/5 FCD minus 40 equals 0. And I'm going to find that FCD is 40 kilonewtons. Except that's not right. I can't do my math clearly. It's going to be 40 kilonewtons times 5/4. So I get force CD is 50 kilonewtons. I got a positive value, so it's in tension. So we are 50 kilonewtons in tension. Okay? Which makes sense. If this is in compression, it's pushing down. So the X component is, the Y component is going down. So if this is going down, this Y component has to be going up equal and opposite, which makes it pushing up in tension. Okay? So now we can sum forces in the X direction. And I have 60 kilonewtons. It is in tension. Behaviorally, it's like positive. But for equilibrium, which is not behavior, it's the rules that we're using for math, this is going to be a negative 60 kilonewtons. Okay, this one's in tension, pulling to the right. And it is at a 3/4. So I have plus 3/5 times 50 plus force CE equals 0. I'm going to keep CE on one side, pull these other using algebra to the other, and I'm going to get 3 enter 5 divided by 50 times, which is negative plus 60, I get that FCE is a positive 30 kilonewtons. And what does positive mean? It means we are at 30 kilonewtons and we are in tension. Okay. Now, if I look at this, if I'm in tension, that means this member is in tension, so it's wanting to stretch. So C and E are having to push back on it. Okay. So if it's in tension, we're pulling on the joint. And by inspection, I can look at EF. If this is 30 kilonewtons pulling to the left, when I sum forces in the x direction, I can find that EF also equals 30 kilonewtons in tension. So we can go down here, 30 kilonewtons in tension. Okay, so here we have the choice of finding unknown DF. Okay, if we know DF, then because this is a right triangle, if I know the x component and the hypotenuse, I will know the y component, which is the reaction here at the roller. If I know the reaction here at the roller based on internal equilibrium, I could also find the reaction based on external, and they should be the same number. Okay, they should work out to be the same number. Again, because nothing moves, everything we do in this class should have a correct answer when you turn it in. So here we have D. My top member is in compression, so we're going to show compression. This member CD is in tension, so we're going to show that tension. Okay, that's a zero force member, not going to have it on there. We have member DF, so force DF, and it is also a 4 to 3. And so if I'm looking at this, if I sum forces in the x direction, I have the x direction here and the x direction here. If I sum forces in the y direction, I have the y direction from this member. Either way, I'm going to come up with FDF. So here's how I can start checking my work. Let's start with summing forces in the y direction. And I have negative 4/5 times 50 minus 4/5 times FDF equals 0. Those go away. FDF does indeed equal 50 kilonewtons, and it's in tension, which makes sense if this is pulling down. Okay, it's in tension, pulling away from. This has to have, wait, that should be negative. See, I got ahead of myself. I'm like, that doesn't make sense at all. If I pull this over, we still have a negative. If I'm pulling down in tension, my y component is going down. In order to meet equilibrium, my y component has to be going up. That has to be a compression member. Okay, so we have 50 kilonewtons in compression. How can I check this? Let's sum forces in the x direction. Okay, so I have a positive 60 minus 3/5 times 50. Okay, this is also going to the left because it's in compression, it's pushing up, so the x component is going to the left. So minus 3/5 times 50 equals 0, and I get 60 minus 30 minus 30 equals 0, 0 equals 0, check. So my joint checks out in equilibrium. Okay, now I found all of the members in my system. If I look here, I can tell this y component, if this is 30 and this is 50, my y component has to be 40. It's a 30, 40, 50 triangle. When I come back over here, AY was 80. 80 plus 40 is 120. So I'm checking external equilibrium. I also found that reaction because it has to meet with my internal equilibrium. And that's a super cool thing about statics is you should never have a wrong answer. You will be able to check everything you do by the end of the problem. You should have already checked several times to make sure you're on the right path. And here we didn't find this reaction, but by finding these two members, we found what that reaction had to be at F. And it had to be 40 kilonewtons. I also can look at this, that if this is 80 kilonewtons, this has to be 40 to balance that 120. Okay, the beauty of statics.